Okay, so welcome back to another video. So we have a combination of both an integral and an infinite product series we want to calculate. So we want to integrate the entire real line of the infinite product series of cosine of x squared divided by n squared dx. So interestingly, the entire step is going to be relying on a bit of complex analysis specifically to utilize the whole manipulation. As you notice that with the product series, we're actually expanding, as you see, the entire, cosine function. And as mentioned with complex analysis, you can guess that we can actually just be utilizing the real / imaginary part, mainly the real part, as if you were to take the real part of Euler's formula, we get the cosine function. So we were utilizing that, so I just gave that first step away. And I think what's interesting is that as the steps progress further, we're actually going to do something what I think is really cool that we want to notice. Utilizing Euler's formula yet again, that it actually makes the computation behind this integral a little bit easier, and you'll see where I'm coming from with this. So with that out of the way, and we got a special function coming up that you guys can kind of know the values of that, as it's been used in so many of my videos. So why don't we actually just jump right in. So let's actually break this integral up. As we know with the cosine function, it's actually just even function. So with this in mind, if we're dealing with even functions over an integral of the real line, we can actually split this up as a double. But let's actually break that smaller and actually just separate this and deal with the half interval of the positive real numbers. So we'll start with the integral from 0 to infinity of just the infinite product series written as above, n equals 1, and then cosine of x squared divided by n squared and then dx. So as you can see that we just want to put in the entire expansion, so we have 0 to infinity, and what we have is going to be cosine of x squared multiplied with cosine of x squared divided by 2 squared. I'm not going to fully evaluate this, we're just going to leave that the way it is just for the sake of the expansion. So cosine of x squared divided by 3 squared, and then we have so on and so forth, infinite of the terms we're dealing with, and all the way n dx. Okay, so as I mentioned, we'll be utilizing Euler's formula. As if we were to take the real part, we actually get the cosine function itself. But there's something you want to pay attention, and this is actually the interesting step that I feel is a game changer. So we know that Euler's formula, e to the power ix, we know that that's just going to equal cosine of x plus I times sine of x. Now, if I were to take into the negative direction, so e to the power negative ix, of course, that's just cosine of x, and then instead subtract I times sine of x. Of course, for that being the case, it's a negative, but if you plug in cosine, that is an even function, and we just get that same function. And meanwhile, sine is an odd function, so that's the negative unit being multiplied to that. So, of course, if I take the real part of both of these functions, so the real part of e to the power ix of Euler's formula, that is, of course, just cosine of x. Then, of course, if I just take the real part of e to the negative ix, then, of course, guess what? That's the same thing. So that's also going to be cosine of x. And we get something of the same thing. So what does this have to do with anything? So as I were to take the real part, we're actually going to manipulate this a little bit differently, as we just shown that both taking the real part of e to the ix and then to the negative direction, they're both equal to both that cosine. And we just manipulate this such that we actually just replace our inputs. So now what we're dealing with now is so far that this is just going to equal to the real part of our integral from 0 to infinity. And so what we have is going to be e to the power negative ix squared multiply e to the negative I times x squared divided by 2 squared, then times e to the negative I, then x squared divided by 3 squared, then so on and so forth, and then all the way up, ending up at dx. Okay, and so with that in mind, so what we can do is that, of course, everything shares the same base, so we can put everything under just in the top of the exponent. So what we have now is going to be just written as follows. So now we're going to have the real part of the integral from 0 to infinity. So of course, this is going to be e to the power negative ix squared, then subtract I x squared divided by 2 squared minus I x squared divided by 3 squared, then so on and so forth, then that just ends off with dx, which of course we can actually factor out the negative I squared, I times x squared. So of course that's just going to yield us with, so the real part, the integral from 0 to infinity of e to the power negative ix squared. So that's going to be 1, and then now add this with 1 divided by 2 squared plus 1 divided by 3 squared, and then so on and so forth. So we have dx, close that off, and you'll notice that this is actually a nice infinite summation, that this is actually what's known as Basel's problem, the Riemann zeta function evaluated at 2. So the Riemann zeta, I wrote that weird. We know that the Riemann zeta of 2, which is just basically just equal to pi squared divided by 6. And so we can actually just replace that, and that actually makes the evaluation a little simpler. So now what we have now is something a little even more simplified. So I'm just going to continue forward over here. So I have the real of the integral from 0 to infinity of e to the power negative I x squared, and then multiply with pi squared divided by 6, and then dx. So of course, something like this, now let's actually perform a little u sub. So I'll let u, actually going to instead call this u squared. So we'll let u squared equals I times x squared, then multiply with pi squared divided by 6. If I were to solve u by itself, so keep in mind that I take the square root of all that, but that means I have a square root of I. We notice that I is the same thing as equal to e to the power I times pi divided by 2. If you look at this at the complex plane using the polar coordinates, of course. So that would have to mean that if I take the square root of that, so u is just going to equal simply just, so to put everything back together, so it's pi divided by the square root of 6, and then multiply with e, or times x first, times x first, and then multiply with e to the power I, and then times pi divided by 4. Now afterwards, doing the differentiation of both sides, so that means du, so that's just dependent on x. So it simply just reduces to just pi divided by square root of 6, multiplied by e to the power I, and then times pi divided by 4, and then dx. So now let's put everything back together. So I have the real, and then of course if you have to change your bounds, but that's not really going to do anything because it's going to remain the same. So it's the integral from 0 to infinity. Now it's just going to be e then to the negative u squared, and then replace our, now okay, we have to replace the dx differential for the new du, so I have to just divide this constant to both sides. So now it's just going to be the square root of 6 divided by pi, then now we multiply this by e, and then to the power negative I times pi divided by 4, and then du. Okay, so we just close this off. Then there's some things that can actually just be factored out, since these are just a constant, so that can just go outside. So now I have the real of, so let's see, the square root of 6 divided by pi, then e to the power negative I pi divided by 4, multiplied by the integral from 0 to infinity of e to negative u squared du. And guess what? We actually know this integral. This is the Gaussian integral for the half real line, which is going to come down to just simply just equal to square root of pi divided by 2. So we can actually just simplify this down. So now we have the real, and well, don't forget that the square root of 6 divided by pi, even if you take that real part, it's still going to be that same value. So now, and then same thing over here, as we mentioned, that's square root of pi divided by 2. So I can actually factor out that side of the multiplication, which yields us so far square root of 6 divided by pi, then times the square root of pi divided by 2, which just leaves us with times the real part of e to the negative I, then times pi divided by 4, which if I plug the pi over 4 back into our Euler's formula over here, and if I take the real part of that, that's simply just going to equal to just 1 divided by the square root of 2. And so that will yield us square root of 6 divided by pi times square root of pi divided by 2 times 1 divided by the square root of 2, which just simply just yields down to 1/2 times the square root of 3 divided by pi. But we're not done yet, because that answer is simply just answering the question of what is the value of the half, which we want to instead evaluate the entire real line. But of course, this being an even function for this, where we split this down, all we have to do is just multiply 2 to this answer, and we get that I being our integral slash infinite product, that combination that we want to evaluate. It's just going to be simply just equal to the square root of 3 divided by pi. And therefore, that actually yields us the final answer of something of a combination that I think is interesting. The interesting steps specifically utilizing that Euler's formula, taking this real part, that we actually have to do a manipulation. As you notice that if I didn't have this step, we would have done something with instead e to the power u squared, which it's pretty difficult, especially you can't really find its antiderivative. Well, you kind of can, but it's, again, tricky. But even if you evaluate it with its bounds, it's actually not that possible, because actually that integral doesn't converge. So with that in mind, there we have it. A simple answer of something, you know, of a combination that's crazy, and just like that, yep. So that's pretty cool if you ask me.